Properties of the trigonometric functions. Chapter 6, section 3. All right, so we've spoken about trigonometric functions. So now we're going to talk a little bit about the properties of the functions themselves, as opposed to just specific values at specific angles. So here's a big table. It looks wordy. It doesn't, not telling you that much. Basically, listing the functions, we're going to call them trigonometric functions. So now they're f of theta, right? Each of these trigonometric functions is a function of the angle theta. For sine, the domain is all real numbers. And the range is all real numbers from -1 to +1 inclusive. Now, I want to point out that when we're dealing with this as a function, we're dealing with it as a function of the angle. We're not dealing with it as a function of x. See, if we were trying to deal with it as a function of x, we'd find out it's not a function, right? It creates a circle. If you're dealing with the unit circle, so that's not a function. But if we do it as a function of the angle, then that angle can go from -infinity to +infinity. So as such, the domain is all real numbers. The range, which is still going to be the output, the y value, is still going to go from -1 to 1, just like on the unit circle. Cosine, domain is also all real numbers, and the range is from -1 to +1 inclusive. Tangent, the domain is all real numbers except for odd integer multiples of pi/2. Pi/2, remember, is 90 degrees. So 90 degrees, 270 degrees, -90 degrees, -270 degrees. And the problem there is you end up with a divide by 0. So it doesn't exist at those points, but the range is all real numbers from -infinity to +infinity. Cosecant, domain is all real numbers except for integer multiples of pi. Again, running into that problem of a divide by 0. The range is all real numbers greater than or equal to 1 or less than or equal to -1. So everything except for from -1 to +1 exclusive. Secant, similar to cosecant, all real numbers except odd integer multiples of pi/2. Again, that divide by 0, but the range is all real numbers greater than or equal to 1 or less than or equal to -1. And then cotangent, domain is all real numbers except integer multiples of pi, and the range is all real numbers. So these trigonometric functions are actually what we call periodic functions, meaning that they repeat themselves at an even spacing. So a function f is called periodic if there is a positive number p such that when theta is in the domain of f, so is theta plus p, and f of theta plus p is equal to f of theta. So that's just saying that if it's periodic, then it will cycle through itself every p, whatever that happens to be. A certain, in most cases, we'll say that's 360 degrees, assuming, or 2 pi, assuming that we haven't modified the function at all. But it just means that if you watch it, it's cyclical and it'll keep going, ending up in the same spot again and again. If you think of a bicycle tire or a car tire, and you look at where the air valve is, as you drive along, that air valve actually creates a sinusoidal wave or sinusoidal function that it starts at one point and then it will continue through a cycle going up and down, reaching its peak value when the valve is at the top, its minimum value when the valve is at the bottom, and hitting all the places in between. And that's a periodic function. One full rotation of the wheel moves that valve a full cycle to where it's back at the same height in relation to the ground that the wheel is rolling on. And that's the same idea here with these, that a full rotation or a full cycle or a full period is the time that it takes to get from one point in the cycle to another point that's the same in that cycle. If there is a smallest such number of p, this smallest value is called the fundamental period of f. So meaning, like I said, 360 degrees for a lot of our trig functions. Well, 720 would also work because if it's in the same spot after 360 degrees that it was at the beginning, then it'll be at that same spot another 360 degrees or at 720 degrees. It'll be there again at 1080. But the fundamental period is that 360, that one full rotation or one full cycle. So let's talk a little bit about periodic properties. So looking at each of the different trig functions, we have to recognize what is the standard period or the fundamental period of it. So sine is periodic with 2 pi being its period. So it'll repeat every 2 pi. That's 360 degrees. So sine of theta plus 2 pi is equal to sine theta. Cosine is the same, that it will cycle every 2 pi. So cosine of theta plus 2 pi is equal to cosine theta. Tangent has a period of pi. Now, that is the fundamental period. Remember I said that if you take multiples of it, those will also give you a period. They're just not the fundamental period. And we will find at times that it's easier to treat tangent as if it had a period of 2 pi. So we'll go through 2 full cycles in one period to allow us to do calculations. But tangent of theta plus pi is equal to tangent theta. Cosecant gets back to 2 pi as its period. So theta plus 2 pi gives us cosecant theta. Secant theta plus 2 pi is equal to secant theta. And cotangent theta plus pi is equal to cotangent theta. So they're cycling around. Now what's interesting with this too is not only that these cycle around, but that these are going to be very helpful to us in a little bit, knowing these to recognize what's going to happen. Now let's talk a little bit about quadrants and what happens with trigonometric functions in different quadrants. You should all be aware that when you're looking at a rectangular plane like this, the XY coordinate plane, that the first quadrant is the one in the upper right-hand corner. That's the one where both X and Y are positive. And then the quadrants are numbered in a counterclockwise fashion. So if that's quadrant 1, then the one to the left, and so left top is quadrant 2, left bottom is quadrant 3, and right bottom is quadrant 4. I will also point out that standard notation for quadrants is that you use Roman numerals. So as written here, 1, 2, 3, 4, I, IV, right? As opposed to putting the Arabic numerals, which are our standard 0, 1, 2, 3, 4, 5 that we use in daily life. So when you're dealing with that, the third quadrant should be done quadrant III, or just III, not the number 3. Now, what this is showing here is the value of the output of the functions in these different quadrants. We notice that in quadrant 1, all functions are positive. In quadrant 2, sine and cosecant are positive. In quadrant 3, tangent and cotangent are positive. In quadrant 4, cosine and secant are positive. And we're going to talk in the next slide about reciprocal identities. But I just want to point here that sine and cosecant are related to each other. So that's why they're both positive at the same time. Tangent and cotangent are related to each other. And cosine and secant are related to each other. So that's why they're mentioned together. Now, the easiest way that I've found to memorize these quadrants and which trigonometric functions are positive in them is simply all students take calculus. All functions, students, sine, tangent, take, cosine, calculus. All students take calculus. And that tells you which of the main trigonometric functions, sine, cosine, and tangent, are positive. That means all other ones are negative in that. So in the second quadrant, cosine and tangent are negative. In the third quadrant, sine and cosine are negative. In the fourth quadrant, sine and tangent are negative. And obviously they're related ones. And we're going to talk about those on this next slide. So reciprocal identities. Cosecant of theta is just the reciprocal of sine theta. So it's 1 over sine theta. And sine theta is 1 over cosecant theta. They're reciprocals. Secant theta is 1 over cosine theta. And cotangent theta is 1 over tangent theta. So that's where, going back into that, we can see sine and cosecant are reciprocals. Tangent and cotangent are reciprocals. Cosine and secant are reciprocals. So if you realize that, then it's obvious that the sign SIGN would be the same for those in any of these quadrants because they're ratios, and that ratios are just division. And if you divide a negative number by a positive number, you get a negative result. If you divide a positive number by a negative number, you get a negative result. So it doesn't matter which way that reciprocal is put, the sign is going to stay the same. Another set of identities, and these identities are on the formula sheet that I've set up for you in Blackboard. So quotient identities, tangent is equal to sine of theta over cosine theta. Remember that we said tangent is equal to y over x. And when we were dealing with the unit circle, we said that sine was equal to y and cosine was equal to x. So tangent is equal to sine over cosine. But even if we're not dealing with a unit circle, sine is equal to y over r, cosine is equal to x over r. You've got that r in the denominator of both the numerator and the denominator of that, which cancels out, leaving you with y over x. So tangent theta is equal to sine of theta over cosine theta. And then cotangent is the reciprocal of tangent. So that's equal to cosine theta over sine theta. So those aren't so bad. Usually we can remember those pretty well. The next ones may be a little more difficult to remember. These are the sum identities. And you've probably seen these before. You may or may not have had it explained to you where they came from or why they are what they are. So I'm going to present them to you, and then I'm going to show you where they came from. So first, we've got sine squared theta plus cosine squared theta is equal to 1. So trigonometric identities here. Very common ones. You see that regularly. One that you may not see as often, tangent squared theta plus 1 is equal to secant squared theta. And then another one that you may not see as regularly, cotangent squared theta plus 1 is equal to cosecant squared theta. Now, like I said, you've probably seen that first one. The other two you may not have. First one's the easiest one for me to remember because it's pretty straightforward. And when I say straightforward, I mean it's something that's easy for me to put together. Sine, cosine, 1. Also knowing that, well, I'll get to that in the next slide, but that one makes more sense to me and stands out as being more obvious. Tangent theta plus 1, cotangent theta plus 1 being equal to secant squared theta and cosecant squared theta respectively, not so much so. But the key thing is, can I come up with it if I need to? And here's how you do that. So we're going to start out and realize that those sum identities are based on the Pythagorean theorem. A squared plus B squared is equal to C squared. Now, if XY is a point on the unit circle, then that point XY we can plug it into the Pythagorean theorem and we get x squared plus y squared equals r squared. Remember, r being the radius. If we're on a unit circle, then r is equal to 1, x is equal to cosine, and y is equal to sine. So I can then substitute r, x, and y with 1 cosine and sine, and I get cosine squared theta plus sine squared theta is equal to 1. And then using the commutative property, I get sine squared theta plus cosine squared theta is equal to 1, which that was that first sum identity. Sine squared theta plus cosine squared theta is equal to 1. And like I said, that's relatively easy. That's y squared plus x squared is equal to 1. So if we're on a unit circle, that's what we're dealing with. So a point on the unit circle puts us y squared plus x squared is equal to 1, which is Pythagorean theorem. So that's the one that, like I said, I find it to be more intuitive. The other two, not as intuitive just to look at them, but as long as we remember that they are based on the Pythagorean theorem, and that using the Pythagorean theorem in a unit circle, we get sine squared theta plus cosine squared theta is equal to 1. Now we can find those other ones relatively simply. Let's divide everything by sine squared theta. By doing that, that's going to turn one of my terms into a 1. And if I do that, I get sine squared theta over sine squared theta plus cosine squared theta over sine squared theta is equal to 1 over sine squared theta. Well, sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. Remember the quotient identities. And 1 over sine squared is equal to cosecant squared, the reciprocal identity. Now, don't get confused by the fact that the identities that we use were cosine over sine, and then I just applied that to cosine squared over sine squared, or 1 over sine I just used for cosecant squared. Keep in mind that the power rule says that if we have a ratio, that we can take the exponent of the ratio and distribute it through the ratio. So if we have the quantity a over b squared, we can make that a squared over b squared. So if we realize that, we can go, wait, cosine over sine is cotangent. So cosine squared over sine squared is cosine over sine, the quantity squared, which is cotangent squared. Same thing with the 1 over sine squared. 1 squared over sine squared is 1 over sine squared, or cosecant squared. But we can see how easily that came together. And then alternately, to find the other one, let's divide by cosine squared, which means we're going to cancel out our cosine squared term, and we end up with tangent squared theta plus 1 is equal to secant squared theta. So not too bad in that sense. I really like it when I can find something or work my way through it to come up with an identity and such, rather than having to try to memorize that. It's much easier for me to go, hey, I know they're all based on Pythagorean theorem, and come up with them that way or derive them, rather than for me to try to remember that tangent squared theta plus 1 is equal to secant squared theta, because that's where I make mistakes and I put in the wrong one. I go, okay, tangent squared theta is equal to plus 1 is equal to cosecant squared. No, that was wrong. Whereas if I do this, I know I'm going to get the right one every time. So let's take advantage of some of these identities and trigonometric function properties that we have to use that for finding the values of trigonometric functions of theta when the value of one function is known and the quadrant of theta is known. So if I'm given a single trigonometric function, the value of a single trigonometric function, tangent of theta is equal to 1/5. Then if I'm told what quadrant I'm in, I can determine all of the other trigonometric functions. Now, the reason I need to know what quadrant I'm in is because there are two quadrants in which a trig function is positive, and there are two quadrants in which the trig function is negative. So just having a trigonometric ratio does not tell me what the actual values are going to be for all of the other trigonometric functions. I need a quadrant to clarify where different trig functions are going to be positive and negative. So the first thing I do to do this is I can draw a circle center of the origin showing the location of angle theta and the point P that corresponds to theta. This is helpful as a visual because then I can see whether X or Y are going to be positive or negative. The radius of the circle that contains P equal X, Y is R is equal to the square root of X squared plus Y squared, right? If I have X, I have Y, then I can use Pythagorean theorem to get R. And I can reverse things too. If I have X and I have Y, if I have X and R, then I can get Y. If I have Y and R, I can get X. So assign a value to two of the three variables, X, Y, R, based on the value of the given trigonometric function and the location of P. Use the fact that P lies on the circle X squared plus Y squared equals R squared to find the value of the missing variable. So like I said, use Pythagorean theorem and solve for whichever variable you're missing. Then apply the trigonometric ratios to find the values of the remaining trigonometric functions. So let's go through an example of this. What if I want to find all trigonometric ratios, that should say ratios, not rations, when cosine theta is equal to 2/3 in quadrant 4. Okay, so the first thing I want to do is I want to make sure that cosine is actually positive in quadrant 4, because that's what this is claiming. All students take calculus. Yes, cosine is positive in quadrant 4. Well, quadrant 4 tells me that X is going to be positive and Y is going to be negative. Okay, so it tells me that. And I know that cosine is X over R. So I can take that and say, okay, X is equal to 2, R is equal to 3, Y is going to be negative, but I don't know what it's going to be. It's going to be negative because I'm in the fourth quadrant. So now I need to solve for Y. So Pythagorean theorem, 2 squared plus Y squared is equal to 3 squared. Trying to get Y by itself, so Y squared is equal to 3 squared minus 2 squared. Y is equal to the square root of 3 squared minus 2 squared. So that's square root of 9 minus 4, which is the square root of 5. And you notice I put a negative sign there because we are in the fourth quadrant and Y is going to be negative. So I guess technically what I could have done is I could have put a negative up in the third, well, maybe in front of the square root of 3 squared minus 2 squared would have been a good spot for it. But basically, I know that it could be either the square root of 5 or negative square root of 5. Since it's in the fourth quadrant, it's got to be negative square root of 5. Now that I have that, I can start building my trig functions. Sine is going to be equal to Y over R, so negative square root of 5 over 3, or negative square root of 5 over 3. Cosine we already have is 2/3. Tangent, negative square root of 5 over 2, so negative square root of 5 over 2. And there's really nothing wrong with leaving it as negative square root of 5 over 2. I'm just, for consistency, putting my negative signs in front. Because really, if you end up with a negative sign in the denominator, that's kind of frowned upon for leaving it in that way. We can use it like that if we're doing calculations, but to leave a ratio with a negative in the denominator is really just a bad form. Cotangent 2 over negative square root of 5, so that's negative 2 square root of 5 over 5. Remember, we've got to rationalize it, and I'm pulling my negative out. Secant 3 over 2, and cosecant 3 over negative square root of 5, or negative 3 square root of 5 over 5, again, rationalizing it. So given one trigonometric function and the quadrant, that gives us 2 out of 3 values that we can plug into the Pythagorean theorem, solve for the other one, make sure you put your sign correctly based on the quadrant, and then just build your trigonometric functions. Odd and even functions. Now remember, an odd function is a function that's symmetric with respect to the origin. An even function is one that's symmetric with respect to the y-axis. So the sine function is symmetric with respect to the origin. So the sine of negative theta is equal to negative sine of theta. Remember when we were finding odd and even functions, if we plugged in negative x into the function and we came out with negative of the function, we had an odd function. If we plugged in negative theta and we came out with the same function, then we had an even function. If we plugged in negative theta and we came out with something that was not the function or the negation of the function, then we had neither. It was neither even or odd. Well, luckily with trigonometric functions, they're always even or odd. So sine of negative theta is the same as negative sine of theta. Cosine of negative theta is the same as cosine theta, because cosine is symmetric with respect to the y-axis. Tangent negative theta is equal to negative tangent theta. Cosecant of negative theta is equal to negative cosecant theta, and that should make sense because that's the reciprocal of the sine function. So obviously symmetric with respect to the origin. Secant of negative theta is equal to secant of theta. Again, should be obvious because it's the reciprocal of the cosine function. So it would also be symmetric with respect to the y-axis. And cotangent of negative theta is equal to negative cotangent of theta. Again, the reciprocal of the tangent function. Now, why do we care about with that? Well, actually, it makes our life a lot easier because it means that we can take negative angles and treat them as positive angles just by pulling out a sign. Or not pulling out a sign if it's an even function. So that's why this is handy to know. It can make our life a lot easier. So that finishes up working with properties of trigonometric functions.